Well, good morning and welcome everybody. Today we are here celebrating the International Day of the Girl, and you are going to be so impressed with the female lineup that we have with some amazing just I can't even speak to what they're going to present share with you with their accomplishments today, but you guys are going to be blown away. But this is our Smart Circuits Lab, and we are so excited to have you all here. And we are not going to waste any time in continuing on with this celebration today. And I'm going to pass it off to our amazing ET staff member, Jillian Williams, who's going to speak on some initiative that we have here at Engineering Tomorrow.
Good morning, everyone. You are in for a treat today. And also, it's so amazing to see all of this girl power on the screen. I want to take just a second to shout out our Girls in Engineering Teacher Advisory Committee, which is new this year. It's a new initiative aimed at supporting our mission here at ET of creating a more equitable and inclusive future for female engineers. And so I wanted to thank these teachers from across the country that are working with us on this very important mission. And Constance, could you hop in to shout out, I think it's All Hallows?
Yes, we're excited that All Hallows is here today. They are just, they are pivoting. They've been in all men's high school for 100 years, right, Mr. Sousto? And they now are co-ed this year. So we are excited that they are part of International Day of the Girl. Back
Yes,
to you.
over 100 years, our first year.
Fantastic.
Fantastic. And we are so excited for everybody to be here. Thank you, Jillian. And it is time to pass it off because we want these students to get into their lab today. We have Lauren Sawyer here who is going to be leading the introduction, and then it's going to be their time to get into Tinkercad, right, Lauren?
All right. Good morning, everybody. Monica, can I share am I a co-host? Can I share my screen? Oh, yes. Okay.
Yes, you can.
Uh, so I'm going to share with you guys my screen. Can everybody see that? Perfect. All right. Well, everybody, welcome to your Smart Circuits Live Lab Day, and it's International Day of the Girl, which is so exciting. I'm going to have a little shout out to a bunch of the women in STEM clubs that I was a part of a little bit later. So, welcome to your Smart Circuits and Embedded Systems lab, where we're exploring two main topics, electronics and computing. And these topics are so woven into engineering. They're so integral. Every single project that I have worked on, we have needed some kind of circuitry to be able to make something powered, and like maybe a drone. I'm building a drone. We need the circuits to connect to the actual propellers to make those spin, or we need a computer on board. And so we need that to feed all the information it's computing in real time to all of the sensors that are on board. That's definitely a big part of something that I'm doing, as I'll get into as an autonomy engineer. But basically, this lab focuses on the combination of hardware and software and everyday things. And it's really important to emphasize collaboration in this lab because you need more than electrical engineers. You need the mechanical engineers that actually build the hardware. You need system engineers who know how it all fits together. So I love this lab because it really emphasizes how much collaboration there is in engineering as a whole. And that's definitely something that I have experienced. So I'm going to introduce myself now. My name is Lauren Sawyer, and I got a bachelor's degree in aerospace engineering from Penn State University. And I actually just got my master's degree in mechanical engineering with a focus on ocean engineering and applied ocean sciences from UC, University of California, San Diego. And that seems like a really odd combination. So what do I do with that now? I am a research engineer at Leidos Innovation Center. And basically, I focus on autonomous vehicles that drive themselves, but out on the ocean. So I work on surface vehicles, vehicles that stay on the surface, vehicles that dive underwater. I really focus on their navigation. So determining how they know where they are in space and in our world and how they make decisions about where to go next based off of, our mission that we give them or any kind of information that they're collecting along the way. And of course, the shout out to International Day of the Girl. This is actually a picture of me when I was 9 years old in Girl Scouts. And I just wanted to give a shout out to all the clubs that have helped me as a female in STEM. I was part of Girl Scouts when I was younger. I was able to join the Women in Engineering program and the Society of Women Engineers, which has provided such a wonderful network to connect with other females and other women who are pursuing STEM careers and STEM degrees. So really trying to celebrate the International Day of the Girl. All right, with that, let's move on to the actual lab that you guys will be doing today. So this curriculum was actually developed by a couple of engineering interns that I had the pleasure to work with, Gigi, James, and Julian. And Christine Budil was actually the lead engineer behind this whole lab in its first version. And since then, it's actually been revamped and redeveloped. And we had the wonderful Jason Burdick and Joshua Feliciano leading that effort with a new team of interns, Brianna, Grace, and Molly. So huge shout out to you guys. You have created a wonderful lab. So now I've been throwing around this term embedded system. So what is it? An embedded system is a computer system made up of hardware and software that completes a specific task. And embedded systems are all around you. You may have an embedded system in your pocket right now. You guys all probably have cell phones on you, and your phone is made up of so many different and small pieces of hardware and software being the code that helps the computer on your phone think and perform its different tasks. And it can complete lots of these different tasks. I mean, think about it. These phones can, make phone calls, we can text our friends, we can take pictures, we can browse the internet, and that's all located in a different kind of, kiosk within the phone's code because it needs different brains essentially to run all of these different tasks. So in the chat, if anyone could just put in ideas of other embedded systems that you guys see around you. I'll give you guys a second to think of some embedded systems. Cars, that's a great one. Yeah, so TV remotes, that's a really good one. It was with smart TVs, our TV remotes are able to do a bunch of different functions. And you guys have probably heard of the universal TV remote, which can control different speaker systems and a bunch of different TVs. So that's a really great identification. The smart board, yeah, so it's got a bunch of different circuits and it's actually got a really interesting calibration system so that when you poke a spot on the smart board, it reads that as, a pen and it can draw whatever you're trying to draw. So a lot of different touch to its computer showing that on the screen. We've got smartwatches, Game Boy. Yeah, those need a really nice, computer and code to run all of the different software that we're giving them as we plug in different cartridges. ATM, nice. Yeah, that's a good one. Awesome. Well, thank you guys for contributing. Those are all great examples of smart systems. And so, obviously the big one is all of our phones, which a couple of you also mentioned, and the smartwatches is a really good modern addition to that. They have almost as much computing power as our phones. They're getting smarter and smarter every day. So some other examples, someone mentioned a Game Boy, which is great because we have an example of an Xbox here. Those definitely need different kinds of code to be able to access the internet. I know the Game Boy couldn't since it was a bit older, but the Xbox and the Switch, do access the internet. Our smart thermostats, they have to think about what our preferences are if we set them to turn to a certain temperature at a certain time. And then, even professional engineers at NASA deal with embedded systems in creating different drones and Mars rovers. And my autonomous underwater vehicles are all different kinds of embedded systems. So it's such a wide array of things that we see in everyday life and in science. So I think I already alluded to this, but does anyone have an idea what kind of engineer works with embedded systems? And you guys can throw that in chat again. And I know that it's already on there, so try to think of, maybe engineering fields that are outside the box. So like my field of engineering is technically called ocean engineers. And because I deal with vehicles that specifically go in the ocean and we deal with embedded systems. I alluded to NASA engineers and aerospace engineers will also deal with embedded systems. So it's really not a solo sport. I can't design my vehicles and design the navigation system without a software engineer helping me to transfer the code that I write to something that the vehicle can use to think. And I can't do my job with the navigation system unless I have the electrical engineers that are actually physically wiring all the circuits of the vehicle together, because I don't know how to do that. I didn't go to school for that. I went to school for my navigation, and they can't do it without me because they need the vehicle to know where it is in space and time. So it's such a team sport, and that's what makes it a really great part of engineering is I love working with other people, and it's such a treat to learn about all of their different kinds of expertises that I might not know about. Yeah, All Hallows shouted out computer science. I need to work with a lot of computer scientists because I write code to solve technical problems, but machines can't read my code. So I love my computer scientists that I work with. So here's your lab overview. Today, we're going to learn about embedded systems, and by doing so, we'll explore some fundamental concepts in electrical engineering and computer science. In this lab, you'll explore embedded systems, electrical engineering, and computer science by learning some basic information about circuits and some circuit components, building some practice circuits online and using these components, using some code to control LED lights with your computer, and then combining everything you learned in today's lab to create a code that models a digital traffic light. So you'll have your red, yellow, and green LED lights, and they'll model how a traffic light works in real life. There's a lot going on in embedded systems. You've got your hardware, you've got your software, you've got your sensors, which basically feed you real world information. And so there's this question of how do you make sense of it all? I mean, it's so much information. So in this presentation, we'll explore the different aspects of an embedded system and how to build them one by one. So together, we'll discover what it means to be an embedded systems engineer. And systems engineers are the people who really are kind of overseeing everything that the technical, mechanical, electrical engineers are doing and making sure that they still have the scope of the project in mind and that all of these puzzle pieces fit together. So without the systems engineer, I, as a navigation and mechanical engineer, might get really, really focused on one part of the project that doesn't mean all that much to the vehicle. And they're really there to pull me out and say, hey, don't forget, this has an end goal and we're trying to fit this together with the electrical system. So is this problem really something we should be focusing on right now? So they're kind of like the puzzle master. They're making sure everything fits together. We mentioned embedded systems like phones as a combination of hardware and software. And first, we'll talk about the hardware of embedded systems. So we'll discover circuits together, we'll explore different circuit components and how you can connect them together to complete a specific task, such as lighting up your traffic light. With hardware in place, then we can move on to the software of these systems and introduce programming to you guys. And that might feel a little scary. Some of you might have programming experience, some of you might not, but we've got a great way to do introductory code and it makes sense. I'm a very visual learner and it helped me understand code a lot better. It made sense how a computer thinks and how that code flows. So we will help you guys with all of your coding experience in this lab. Finally, as an extension, we're going to add what are called sensors and actuators to our system to allow it to interact with the outside world. In the end, we want a system that can take in information, process it in our circuit and in our code, and produce a result in the physical world. So, all that being said, we're going to start with part one, which is the hardware basics and circuit concepts. So that means we have to start with, what is a circuit? A circuit is a path for electric charge to move, or for electrons to move through a set of wires and resistors, etc. Electric charge moves around the path from device to device, and charges transport energy from one device to another. We can design how our circuit is wired to control the movement of charge and energy from one device to another, and we can manipulate the two to accomplish a task, like lighting up a light bulb. So I have a demo of this all prepped. It's in this circuit construction kit by the PhET website at Colorado. And if you guys haven't used the PhET website, I remember using it a ton in high school. It's great for online lab learning. But basically, what I want to show you guys is here we've got my battery, and this is what provides the charge to the circuit. I've got wires connecting it to my light bulb, which is right here. And then I've actually got what's called a switch right here. And that basically determines, like a light switch, whether I want the light bulb on or off. So now I've got the switch connected, and you can see that the light bulb is on. It is allowing the flow of electricity to go through the circuit and through the wires. I click it again, and it actually is stopping that flow, which means that none of the electrons can get to the light bulb itself. So the battery acts as our source of energy. It's flowing, and what's really cool about this is you can see the direction that the electrons are flowing. So the charge is flowing through the negative end of this battery, and then it's going through the light bulb, and then it's returning back to the positive end of the battery, creating that full circuit. And that's how our batteries get drained of charge, is all the charge that's built up on that negative end ends up going to the positive end, and you can recharge batteries by doing a reverse circuit and moving all those electrons, forcing them back to that negative end. So that's an example of how our circuits are going to work, and how that's a very simple circuit, and basically just the idea behind how electrons flow through wires and resistors. So now we're going to cover Ohm's law, and we're going to dive into what happened when I closed that switch a little bit. So when I opened the switch, the current was not flowing in the circuit. There was nowhere for the electrons to move. And when I closed it, it was moving. And I already alluded to this, but when charges move around a circuit, we call that a current, like a river current. We've got water moving from one end of the river to the other end of the river, and it's creating a force that if we were to stand in the river itself, it would feel like it's pushing us towards the lower end of the river. So it's the same idea for that word current with electron charges. And so how we measure current is super important, because we want to know how much current is going through a circuit, so that we can be able to determine if it's got enough current to actually light that light bulb. So we measure that in what's called amps, AMPS, and we abbreviate that with just a capital A. And the number of amps tells us the rate of the flow of those electrons. So how fast those electrons are moving through our circuit as a whole. If I have a lot of charge moving around, I have more current and more amps moving through my circuit. And then the battery has a certain limited amount of energy. It's not going to have an unlimited source of energy. So we actually define that as a different term, a different unit, and we call that voltage, which you guys have probably heard of. And that's just the measure of how much energy is stored in the battery. So the current is determined by the other parts of the circuit that are connected, but the battery only has a certain amount of voltage, a certain amount of available energy to it, no matter what else in the circuit is connected. So we need sorry, we need a device to supply our energy or supply the voltage, and then we need the voltage source, and that was our actual battery. And then the final thing that every circuit needs is something that causes resistance to move through it. And this seems counterintuitive because we think of resistance as a bad thing. You know, when you're trying to get a project done and you're met with resistance, that usually means someone is pushing back or someone is taking up your time. And that's not always a good thing. But circuits actually need this resistance. Otherwise, the electrons aren't going to move. They're actually pretty happy just sitting where they are. You know, they're chilling in the battery. They're having a good time. They don't want to move. We add a certain amount of resistance to the circuit and they realize, oh, it would take a lot less energy to be chilling on the positive end of the battery, and that causes them to move. It's like if we were to try to roll a ball on a straight piece of land, ball doesn't want to move. There's nothing causing the ball to move. But if we had it rolling down a hill, we placed it at the top, it wants to be at the place where it's not going to try to move again, at the bottom of the hill. And that's the same concept for resistance. And so that light bulb acts as the resistor in our circuit, and it causes a current to occur. And that's what actually lights up the light bulb. So we measure resistance in a unit called ohms. And ohms is the same as Ohm's law. And it's got a weird Greek symbol for anyone who's studying Latin in high school. It's the Greek letter omega. It's totally fine if you have no idea what that looks like right now. But the scientist Ohm discovered that, you know, we need this resistance to make electricity flow. And so he found out an equation that I'm going to be able to show you, which is Ohm's law, which means that the current is equal to the voltage divided by the resistance. So the current is determined by how much voltage you have, how big your energy source is of the battery, divided by how much resistance there is in your circuit. And so less resistance means more current, and more voltage means more current as well. So therefore, as resistance is increased, the amount of current will decrease if you keep the voltage constant. So they're inversely proportional. So before our battery burning up might have remained a mystery for us, but now that we have some concepts to help us analyze voltage, current, and resistance, we can use these to explain why a battery might lose energy. So if we lowered the resistance of the light bulb to too much, the battery's voltage is constant. It's a 9-volt battery in this instance. And that means that the current is very, very high. And this is actually detrimental to a circuit. If the current is too high, it breaks or, burns the circuit. And that's why we see, little sparks come out of different kinds of circuits. It might cause the battery to catch fire, actually. This is called a short circuit, which you guys have probably heard of. And a short circuit occurs when a current with very, very, very low resistance travels through a circuit, which results in the current becoming excessively large. And the short circuits are usually unintentional, but they can damage our devices. They can damage our homes. They can start electrical fires because that current is there's just too much energy flowing through the system. Since short circuits occur when there's a path in our circuit with too low resistance, we need a way to be able to control and add resistance to places in our circuit that needs it. So this is how we came up with the resistor. And this just makes sure that our current is staying at a nice rate of flow through the system. And so in 1959 and 1961, African-American inventor Otis Boykin received patents for his solution to our short circuit problem, the electrical resistor, which you see here. A resistor is just a bulky wire with some added resistance to reduce the current flow through it. You can think of this effect of adding a resistor in terms of pipes and water flow. Adding a resistor is kind of the same as making the pipe smaller, which condenses the amount of water that can flow through it. It makes it harder for the current to flow through it, which makes the current slower. And so this means that our circuits are protected from that kind of damage. So now we're going to identify circuit construction, which we a little bit got into with just that FET diagram, but we're going to add the idea of resistors. So you guys have 4 components to your circuits, and you've got your resistor, you've got your microcontroller, which don't worry, we haven't covered yet. You've got your breadboard, which we will also cover, and then you've got your LED light, and this one might be a little more familiar. This is our light bulb. So now we're going to cover the microcontroller. So the microcontroller is a voltage source for our circuit that we can control with code that we write from the outside. The power comes from a voltage source, like a battery. It's a different kind of battery, actually, that is embedded onto the microcontroller. The microcontroller itself is actually a version of an embedded system. So embedded systems range from all the small parts that we use to create more embedded systems to the Mars rover itself. I mean, they're kind of just built on top and on top of each other. So the battery within the microcontroller, an example of an embedded system. And then the analog in is used to take signals in from a sensor. Sensors read information about the environment around us, and then it records and stores data as a voltage signal. This might seem a little bit confusing, but we'll keep explaining. And then the digital is a source of voltage that you can turn on or off. So it's a battery with a switch. You know, you can control whether that power source is on or off. And the essential question is, how can we use this Arduino with code to transform our ordinary circuits into embedded systems? And so how can we use code to transform our circuit, which is just running by itself, into a smart circuit that we can control without physically touching the circuit that we've created? Now we're going to talk about the breadboard, which is the other kind of confusing thing that we've been introducing in this lab. So the breadboard is a plastic case designed to prototype circuits quickly without the need for manufacturing. They're arranged in electronically connected sections, so it's actually going to matter where you put the connectors on a breadboard in terms of how the current is going to flow. And then these are the LEDs, which I mentioned are like the light bulbs of our system. LED stands for light emitting diode, and it's a device that emits light when current runs through it. And all diodes are polar, which means they have a positive end and a negative end, just like a battery, which allows current to only flow in one direction. So now we're going to embed logic into our circuits, which is basically the hardware and the software combined. So I'm going to introduce you guys to the coding design process. And this is a very circular process. It's a cyclical process. It never truly ends, much like the engineering design process. First, you identify what problem you're trying to solve. You're going to design how your system or your code will fix that problem. And then you're going to write the code itself. And then once you write the code, you're going to identify problems or bugs within the code. So development of code follows this process, just like the engineering design process. It's iterative, and something can always be improved if you're looking for it. Coding is a process, and I actually still use this process today, especially with the flowchart and the pseudocode. And I'll explain what pseudocode means. You're basically trying to translate our thoughts, our human thoughts, into thoughts that a computer can understand. So you're translating a language. And that's not always easy to do just by sitting down and typing out in the computer's language. So it's always a great idea to start with what you want your code to do in terms of a flow chart. So like here, you've got it begins, you initialize some variables and some pins, and then you've got a loop that says, hey, while I've said this loop needs to be on, I want you to turn the LED on, delay, turn the LED off, and delay. So that seems pretty natural. It seems pretty intuitive. Translating that to what the computer can understand can be a little bit more tricky. So I always like to start with writing pseudocode, which basically means taking all of this and turning it into what I want it to do. So while I'm running the code, turn LED on, wait a second, turn the LED off, wait a second. It's going to cause the light to blink. And then we're going to go into the block coding, which is the really visual way to understand how coding works. It's taking this pseudocode, you arrange the blocks right here, and you're able to use language that you speak, the blocks translated into computer speak, and you can kind of understand what you're telling the computer to do. It's very helpful for starting out coding, and actually I even used it when I was in college because I wasn't that good at coding when I was in college, and block coding was a great tool to help me understand what I was actually telling the computer to do. So you guys are going to start with a demo of a blinking circuit, which is just this turn light on, turn light off with a delay in the middle. And you are going to do this with Tinkercad. And so make sure that you are clearing your breadboard in between each runs, writing a copy of the blinking code from the previous slide, making sure to select the right pin number. This is going to be really important because the pin number on the lines of the breadboard will actually determine which of the circuits is getting turned on or off. If you select the wrong pin number, it's activating a pin that the LED isn't attached to. So it's actually working, but your LED isn't seeing anything because it's working on the wrong circuit. And then you're going to use the Arduino to act like a programmable switch and opening and closing the electricity on and off to turn that light on and off. You'll press start simulation, and then you'll mess around with the code to see what else you can do. Beyond that, you guys are going to then program a traffic light. So you'll have 3 LEDs now, red, yellow, and green, and you'll have to determine how to get them to blink in time such that you have the red light only, the yellow light only, and then the green light only, just like a traffic light. If we were sat at an intersection and we had a red light and a green light on at the same time, it would be really confusing. I don't think a lot of us would know what to do in that instance. So we want to make sure that only one light is on at a time, and that we can make sure that we cycle through them, because, you know, we never see a yellow light go to a green light. If the light turns yellow, we're expecting red next. And that's important as a society because it lets us know what order the traffic lights are going in. You know, if I'm stopped, I know I'm going to be able to go green next. I'm not going to sit stopped and then have a yellow light flash at me. I would be very confused. So you want to make sure that they go in order and that only one of them is on at a time. So all that being said, I know this seems like a really daunting task, and I want you guys to just play around with Tinkercad at first because it's a really great and powerful tool, and you can do so many different things with Tinkercad. It's a great simulation for, you know, this messy breadboard in real life. It kind of cleans it up for you. It's a great introduction to breadboards. And if you feel daunted by this task, we have so many different people available to help you, myself included, but we have a ton of different engineers and leaders who are here to help you guys with creating that smart circuit. So please, please, please ask questions. Don't be intimidated. This is a great lab. It can be a little challenging and complicated at times, but it's so worth it. And it teaches you so much about the world of engineering. So that is your introduction, and I am going to hand it off back to Monica.
Well, I want to say, first of all, a round of applause for Lauren doing such a great job sharing her background, her story, her amazing STEM journey, and introducing this amazing lab to us this morning. I want to say we are going